All right, let's dive right in. Today, we're talking about one of Rust's most game-changing features, how it handles asynchronous programming. We're going to explore the massive engineering problem Rust had to solve and how it did it while staying true to its core philosophy of zero-cost abstractions, which is really just a fancy way of saying you get powerful features without paying a performance penalty. But before we get into the weeds, let's start with the big question that drives this entire story. How on earth can a single computer, a single server, possibly juggle tens of thousands of different conversations at the exact same time? Now, this isn't some abstract puzzle. It's the fundamental challenge for basically every modern web service you use, and the answer has literally shaped the internet as we know it. To get there, we first need to understand the problem that kicked this whole revolution off, what's known as the C10K crisis. The C10K problem, a name coined all the way back in 1999, is exactly what it sounds like: handling 10,000, or 10K, connections at once. But the key insight here, the real light bulb moment, was that the bottleneck wasn't about raw CPU horsepower. No, it was about how efficiently a server could manage all those connections, especially since most of them are just sitting there, idle, waiting for something to happen. So what's the most obvious way to handle this? The simplest thing you can think of? Well, you just tell the operating system, hey, for every new connection, to spin up a brand new thread. It makes the code super simple to write because the OS does all the hard work of scheduling for you. If one connection is waiting, the OS just swaps in another one to do some work. Sounds easy, right? Well, let's see what happens when we try to scale that simple idea up to our C10K goal. We've got our 10,000 connections ready to go. Now, here's where the trouble starts. On a pretty standard system, every single one of those OS threads reserves about 8 megabytes of memory just for its own little workspace, its stack. And, yep, you can see where this is headed. 10,000 connections times 8 megabytes a pop, that's a staggering 80 gigabytes of RAM. And for what? Just for thread stocks that are almost entirely empty, just sitting there waiting. The model is already completely broken on memory alone. But here's the crazy part. The memory usage, that's actually the lesser of the two problems. The real performance killer is the CPU overhead. Every time the OS has to swap between these thousands of threads, it does something called a context switch, which is pure wasted work. Even worse, it messes up the CPU's super fast cache, meaning it has to fetch data from slow memory all over again. At the C1K scale, your server ends up spending all of its time just managing the threads, not actually doing the work you want it to do. It just grinds to a halt. So, clearly, a totally different approach was needed. The entire industry had to make a huge paradigm shift, moving to what's called an event-driven model. Instead of dedicating a thread to wait for each connection, this new model basically asks the OS one simple question over and over. Hey, has anything interesting happened on any of my thousands of connections yet? The system only wakes up and spends CPU cycles when there's actually work to be done. And this is the model that Rust had to embrace. So how did Rust's first attempt at this go? Well, it led to a period that developers fondly refer to as Combinator Hell. And trust me, that name is well-earned. The whole system was built on a foundational idea from a library called futures, the future trait. You can think of a future as basically a promise. It's a value that represents some work that will be finished, well, in the future. But it's lazy. It does absolutely nothing on its own until something called an executor comes along and pulls it, basically poking it and asking, hey, can you make any progress right now? Now, to chain these promises together, to say, do this, then do that, you had to use these methods called combiners, like .then or .select. And for anything even slightly complex, this turned your code into a deeply nested, tangled web of closures. The logic, the actual flow of your program, became almost impossible to follow, let alone debug. This right here, this was Combinator Hell. This quote just captures the feeling perfectly. Rust's big promise was fearless concurrency, because its famous borrow checker got rid of memory bugs. But this new combinator pattern, it just introduced a whole new set of fears. The compiler errors were terrifyingly cryptic, and the code itself was a disaster. So Rust had a solution that was fast, but it was just awful to use. But that pain, that ergonomic disaster, it forced a multi-year effort that led to a genuine breakthrough. So welcome to what I like to call the async/await illusion. Just look at the difference here. It is absolutely night and day. On the left, you see that twisted combinator code we were just talking about. On the right, doing the exact same thing with async await, it just looks like normal, clean, sequential code. All the horrible nesting is gone. You can just read it from top to bottom. This was nothing short of a revolution for developer productivity. So what's the magic trick here? How is this even possible? Well, this is the secret. Async await isn't some complicated feature running in the background. It's purely what we call syntactic sugar. The Rust compiler takes that simple, beautiful code you wrote, and at compile time, it completely transforms it into a super optimized, low-level state machine. You, the developer, just write your intent, and the compiler does all the hard, error-prone translation work for you. A really fantastic way to get your head around this is the chef's recipe analogy. Think of your async function as the recipe, the list of steps. Now, when the chef, our CPU, gets to a step where they have to wait for water to boil, that's an await point, what do? They put a bookmark in the recipe, that's our state machine, and the kitchen manager, the executor, immediately hands them a different recipe to work on. Then, when the kettle whistles, that's our waker, it signals the manager that the first recipe is ready to go again, right from where the bookmark was. Absolutely no time is wasted just standing around. And this incredibly elegant solution isn't just a nice convenience. It is the ultimate expression of Rust's most important design philosophy. It is a true zero-cost victory. The principle of zero-cost abstraction is this core promise in Rust that you shouldn't have to choose between writing code that's easy to read and writing code that's fast. They should be one and the same. The elegant, high-level features you use shouldn't add any performance overhead compared to if you had painstakingly written the low-level version by hand. So, how does async await actually achieve this zero-cost goal? Well, a few key things. First, Rust has no garbage collector, which means no unpredictable pauses at runtime. Second, the language designers purposely rejected other solutions like green threads because they came with hidden performance costs. And finally, and this is the genius part, that whole state machine the compiler generates is just a simple struct whose size is perfectly known at compile time. The cost is paid once, upfront, during compilation, not over and over again while your program is running. What this all adds up to is that developers get the whole trifecta. You get the raw performance needed to solve that C10K problem. You get the bulletproof memory safety that Rust is famous for, and you get the control and clean ergonomics of writing simple async/await code. And because the language itself only provides the core pieces, it allows a whole ecosystem of different async runtimes, like the popular Tokyo or the minimalist Small, to exist and be tailored to whatever you need. And this whole journey really leaves us with a final, fascinating thought. The story of async await in Rust isn't just about code. It's about a deep partnership between the programmer and the compiler. So you have to wonder, is the compiler becoming our ultimate collaborator? Is it evolving into a tool that can take our high-level human intent and just flawlessly translate it into the most perfectly optimized machine code possible? It's a powerful idea to think about.